suppose we are simulating activity at a local restaurant. People arrive in groups of various sizes, want a simulation that produces the similar behavior. So this is actually X, or the random variable is arrival per party with a defined frequency, and from that frequency we have estimated the relative frequency for each arrival of each group, and then we also calculated the cumulative frequency. So what is the difference between relative and cumulative? Cumulative is just the sum of the previous value, and that's all. So just like CDF and PDF, so this could be thought of as a PDF, and this could be thought as a CDF for that particular probabilistic process. So arrivals per party could be a group, or could be a single person, or a group of 2, or a group of 3, till group of 8. So how to generate that code, and then look at what's actually happening. So so we try to do the same, or simulate the same, by using the Excel sheet. And the formula is, if D1 is, say for example, you can see, let me double click it. If D1 is less than greater than or equal to 0 and less than 0.1, why I put 0.1 over here? Then put that print 1, otherwise print NA. You can print anything. I mean, you can write this event or something. Or event happened. Need to copy and paste it to all. So leave it for one. I mean, in order to do that, you need to copy and paste event happen in each of the eight lines, and I don't want to waste more time on that. So it says that if D1 is between 0 and 0.1, less than, so there is not equality over here. If D1 is greater than or equal to 0 and less than 0.1, print 1. So 1 means that thing happened, and otherwise print NA. Similarly, over here it says that if D1 is greater than or equal to 0.1 and less than 0.7, print 1, otherwise not applicable. And if D1 is greater than or equal to 0.47 and less than 0.62, then 1. So from where these numbers are coming, 0.1, 0.42, 0.67. So these numbers are coming from that slide. So if you look at the table, so 0.1 is over here, 0.47 comes from the second row, 0.62, and then 0.86, 0.9, 0.94, 0.96, and 1. So if any number between 0.96 and 1 happens, it means that there are 8 people coming at that point. So if I refresh it again and again, you can see that. So I will get different random numbers, and on the basis of these different random numbers, I could recalculate the events again and again. So you all have this sheet uploaded. I think I did it yesterday. So is this understandable now, or is there any question in that?
सर अगर रेगुलर इंटरवल से जनरेट करने हो नंबर्स, ये तो रैंडमली हो रहे हैं ना?
रेगुलर इंटरवल से डी में या बी में? यू टॉकिंग अबाउट डी और?
सर जैसे रैंडम नंबर्स ले लें 0 to 100, उसमें से 10 नंबर्स जनरेट करने हो रेगुलर इंटरवल से, रैंडमली नहीं लेने हो, ये वाली कमांड नहीं लगानी हो फिर से?
नहीं, तो आप, इसका मतलब है आप मुझसे ये कह रही हैं कि in a party, if you go to a party, so let's translate your question into the real world process. So what Maham is saying, that what if we don't have random numbers being generated, rather than we have sequence of numbers being generated? So that would be quite hard to estimate, because in a party, so what you are saying, what you are translating my problem in is that they would one people will come, and then after some time 2 people will come, and then after some time 3 people would come, and then after some time 4 people will come. Yes. Is it possible?
Yes sir.
It's not possible.
Okay sir, thank you.
It's highly unlikely. It's highly unlikely that people come in groups of increasing numbers. It's highly unlikely. I think the more likely question is that, okay, a single person come, and then a group of 3, and then a group of 5, and then a group of 2, and then a group of 3, and then a group of 4, and then a group of 7, and then a single person, and then a group of 2, and then a group of 7, and then a group of 8. I think these random assemblage of number would suit to the real world situation a bit more, rather than a, it's not any regimented thing. We are not we are looking at arrivals, or the size of the group at a certain arrival at a party. We are not looking at something which is a bit more regimented or sequential. So that's why I use the random numbers over here. Does this make sense?
Yes, sir.
Okay. Anyone else? Anyone else facing a problem? You can always download that sheet in your desktop or on your laptops, and then you can always try what's actually going on. So look, we have 0.862078. So if a number is 0.86, so where comes 86? So 0.86 is greater than 0.86, but it is less than 0.9. So it means that I'm looking at a group of 5. Once again, so the number is 0.4977. So if I look at the table again, 0.4977. So 49 is greater than 0.47, and it is less than 0.62. So it should be 3 arrivals. So 1 should be printed in front of 3, and so on and so forth. So what your assignment is to say, for example, let me run it, and then I will just finish it. I will take 1 or 2 more minutes, and then I will finish this topic, and we will go to the next topic, which is more towards modeling and real simulation. So if I need to write the random assemblage of people coming, and I say, do you want to simulate it for about for if you go at the counter or at the entrance and look at the groups, so which groups arrive at the first 10 consecutive groups, and what size of the group would you expect? So let me run it 10 times. So let's assume the first group was of 3 people. So group size, so if I write down the count, 1, 2, 3, I'm looking at the first 10. So for first, when I saw, the group was of size 6, and then when I refresh it, the group was of size 5, and then the group was of size 3, and then the group was of size 2, and then the group was of size 4, and then 4 again, and then 3, and then again 3, and then again 3, and then again 4. Is there anyone who can tell me why 3 and 4 are being repeated so much? Is there anyone in the class who can tell me why 3 and 4 are being repeated so much? And if I do it again for you, let's run this simulation second time. So it is 8, and then 4, and then 2, and then 2, and then 2, and then 2, and then 4, and then 4, and then 5, and then 4. Why 3, 4, 2? These numbers are repeated more than the other ones. So you haven't seen 7, and we haven't seen 1. Isn't that the case? Yeah. I haven't seen the group of size count. Is there anyone who can answer this question?
Sir, it's more common to see people go in a group of 2, 4, 3, but people usually, large groups are very rarely going together.
Yes,
Just on the basis.
this is a very good reason. But could you please justify it from here? This is actually what's happening. The answer lies in the relative frequency. The answer lies in the relative frequency.
Yes, 2 has the highest relative frequency, 0.37.
So 37% of times, 37% of time from this total data, how much is it? I don't know. I mean, I need to sum it. But from this frequency, almost 37% of time, or 37 times, what happened is the group of size 2 came, and 15% group of size 3 came, and for 24%, a group of size 4 came. But the probability of a group of size 5 is 4% only. Same for 6. The probability of a group of size 7 is 2% only, and it is 4 for size 8. The probability of getting a single person is 10%. So that actually this probability is shaping up the group size that are coming as a random. So does this, I mean, is this exercise understandable? So we can simulate it again and again and again and again and again and again, and we can expect what type of group we would be getting in a certain during a certain time interval. So that's actually an important point to make by using the simulation. So this type of, so one more thing is group size bounded or not?
Sir, bounded hai.
What is the lower bound?
Sir, 1.
What is the upper bound?
8.
Okay, thank you very much for the answer. So the group size is bounded. The lowest number of people in the group is 1. The highest number is being 8. We know that it is known, it is bounded. We know that it's an integer. You cannot have 1.5 people coming. So it's a positive integer. But what makes it random? What makes it a probabilistic process?
So we cannot anticipate the number of the number of people in the next group are having there. We cannot anticipate that whether it will be 4 or 5 or 3 or 8. We cannot anticipate that.
Thank you very much. We have, although we have fixed probabilities or fixed chances or we know that the probability of a certain number of people in a group is higher, and the probability of certain number of people in the group is lower, but we cannot anticipate. We can anticipate, but we cannot exactly tell what group of people would be coming next. That's why it's random. So this is the very basic of discrete event simulation. This is the very basics of discrete event simulation. So what event would happen next? So the question would be, what event? In this case, the event is people in a group, the number of people in a group will happen next. This is the question around which discrete event simulation is all crafted. What event will happen next? And if I add one more question, it would be which would be better, I think. If I add one more question, at what time the next event will happen? These two type of questions are actually being answered or are being investigated in a discrete event simulation. In a discrete event simulation, we look for these two questions. Sometimes a discrete event simulation is built only on question number 1. Sometimes discrete event simulation is built on question number 2 and question number 2. Question number 1 and question number 2. So we need to think about which event will happen. And another interesting question would be at what time the next event will happen. So we also need to drive. So we can also have a random variable for time, and we can also have one more random variable which will give you the inter-arrival times. So that those times would be inter-arrival times. So I will go to the NetLogo simulations just to show you a couple of quick simulations. So if you look at the models, say biology would be. So have you seen outlines? Yes, we have seen an autumn. I think a very relevant simulation would be disease spread. Okay, now if you look at the simulation over here, and I just need to set up so we can see a setup. So there are a lot of people that are actually gray. Gray means they are susceptible. They are prone to infection. Red means they are infected. So these two, there are 3 red people, so number of infected is 3. So if I set up it again, so for every resetting, it generates a random assemblage of 200 people. Out of 200, 3 are infected. So if I set up it again and again and again, so you can see that it's a random assemblage over a grid. So there is a grid of you can think of that black background as a graph paper, and for every setup there is a random assemblage, and there are 3 people which are infected out of 200. I can set it up to say 321, and you can see that the random assemblage is of 321 people in that example. Now if I look at 136 people, you can see lesser people over the grid. Now if I set it to go, then you can see that people are mixing, and then the disease is being spread, and the graph of infection versus time reaches when it reaches to 100% of the people. So 1 means 100% over in this case. So when it proportion, so when it reaches to 100% or full people, the simulation would stop. If I set up again and then run go, you will see the same result. Set up again, set it up again. I would increase this, set it up again and then go and set it up again. So one thing we are quite certain about is for every new setup, the assemblage is random, and there are only 3 infected people that are placed randomly over the grid. So there are a couple of things which we can always think of, and then so if there are 136, and you can see that at the end infected becomes 136. That's why the proportion becomes 1. So if I increase the people 272 and then set up it again and then see what happens. So similar result, but it happens a bit faster. Can you anticipate that? So if I set number of people to say 79, then we will get the same result after a certain time delay. If I set number of people to say 392, so curve gets smoother, and then we have results really quickly. And if I set it to say 50 people, the curve is not smooth at all. And then it will take a significant time to build infection. Ji Janab, what are your observations on this?
सर नंबर ऑफ पीपल जब कम है तो उनमें सोशल डिस्टेंसिंग दिख रही है अभी शायद.
Thank you very much. This could be thought as an excellent advocacy for social distancing. This could be thought of as this is a very, very simple setup. I mean, I'm not looking at, people don't wonder like particles in a glass of water, molecules of water in a glass. We don't do that. But you can see that from a very simple setup, from a very basic simulation, we can go to really good results. So this is very important, first thing. Second thing is, if I see a network, so you can see that there is a network now. For every setup, there is a random assemblage of network. So some people are connected, some people are disconnected, and out of 50 people, any 3 are infected. So let me press setup button again and again and again and again, so you can see the people connected. So the people connected are shown by a network. So what would happen to these 5? Would they get infected? No. Why? Why?
सर क्योंकि ये इन्फेक्शन से डिस्टेंस फाइन तो इसकी
Because in our simulation setup, we assume that the disease would only spread via network, and they are not connected to any network. So if I run simulation, you can see that people are getting infected, and it reaches to an infected capacity of, or the, you can see the carrying capacity of 11, and then it stops. So even if they are standing side by side, they are not. If there is no network, they are not connected. Okay, let me stop it, set it up again, and then see how many would get infected at the end. At this time, 18 would get infected. So this is actually how disease spreads in certain networks. If I increase number of people to 500, oh God, and then see. So you find 115 in this setting. If I set it up again and again and again. So in this case, due to connections between the network, there are only 9 infected. If I set it up again and again and then see. So there are almost 158. So still in this case, the people which are not connected to anyone, they are actually safe from the infection. If I look at the environmental setup, I don't know what's actually environment. So okay, so there are patches of people as well. So yellow color denotes the patches. So if I set it up, so there are few people. Oh God. So if there are few people at certain patches, if I decrease the number of people, you can see. So the point. So over this grid, the traveling of any infected person is actually, this shows you the movement of patches as well. So in any case, we have seen some really easy examples. Then let's now not go towards the detail of environmental, because I need to define you the concept of patches and then local and global extinctions. So don't go over there. Let's again go to the network and then try a couple of more things. So let's assume that we have 250 around people, and then if we increase connections per node, can you see this tab? So it was initially 1.2. So if I increase it to 2.9, do you notice the difference? So the more the connections per node, the tighter the network is. So if I run it again, so you can see that everyone will get infected really quick. But if I decrease the connection per node to say 0.2 and then let it run, so infection won't spread at all. So there are 3 people, and out of 1, this actually infected it. In fact, his connections, and that's all. So total infected are 4, and then the simulation is a standstill. Similarly, there is no spread over here. Okay, do we have a message from here? Abhi, do we have a message from this example? Okay, so I need to end my lecture right now because of a couple of reasons. Because I didn't have much time today. Anyways, I think today's lecture is interesting. I will try one more session. Let's see when. And I will try to upload a couple of recording of one lecture related to discrete event simulation. We will go to that in the next lecture. Before leaving, there is one thing I really want you to do is I will share you some material related to discrete event simulation, which is like that. I think it is like that. Just one slide. Yes. These slides actually are so this slide, all of this slide actually we look at discrete event simulation. So you will look at it. It's a simple processing system, arriving, parts, queuing, first in, first out, and then machine server, part in service, and then departing. So this is a very easy example. And then we need to look at a couple of things. So the part number. So the parts are just like the counting, arrival time, inter-arrival time. It's a difference between them, and the service time is actually the sum. How long will it take it to actually get service? So it's not inter-arrival, it's independent of inter-arrival, and it's independent of arrival time. Service time is another thing. So we need to stop when 20 minutes of simulated time has been passed. So this is an example of a discrete event simulation. And just try to I don't know, I mean, I know that it's a bit hard, but just try to go over these slides. I will share them with you after this lecture. So, and try to go over here, simulation by hand setup. So they did all the simulation by hand. So, and you can see that inter-arrival times are changing. So system is looking at part number 2 right now, and then the system is looking at part number 3 over here, and then at part number 4, and then part number 5, and then part number 6, and then part number 7, and it won't service part number 7 because T actually reaches at 20. So at 20 minutes or 20 seconds, whatever the unit was, we need to stop the simulation. So we can run it again and again, and then we can take really good information out of it. So it's a slightly complicated extension of what we did for our in our Excel sheet. So they actually calculated a couple of variables called Q of T, called B of T. They've calculated they have the event calendar. Event calendar is nothing. This is piece. This is the time of arrival, and this is the either the piece is being departure or being arrived. What is the area under B of T? What are B of T and Q of T? If I go back really quickly. So average waiting time is actually called total production is called T, and Q of T is number of parts in a queue at any time. Similarly, B is the utilization of machine. So if machine is busy, B would become 1, and if machine is idle or not working, machine is 0. We can have many other possibilities, but we look at only 2 possibilities right now. So this is a very easy example. It's easy, but it's a bit laborious to go with. So kindly try to read this lecture before coming to the next class. And these are some simulations by hand. And from these simulations, we have estimated the average waiting time in queue, time average number in queue, and utilization of the press or the machine servicing. And that's all.